We've talked about direct proofs and we've talked about proofs by contrapositive. Today we're going to talk about the third major type of proof that we're going to use to prove a statement if P then Q. So whenever we have some statement R of X that's made, and R of X is usually of the form P of X implies Q of X, and it's over the domain of every element in a set. So we have the statement R is for all X in S, P of X implies Q of X. And the way we say that is let X be an element in the set, then if P of X, then Q of X. So in direct proofs and proofs by contrapositive, we always were working from P to Q to show that R of X is true. And we were always working towards showing that R of X is true. So in a proof by contradiction, what we do is we take that statement R and we instead assume that it's false. So if we assume that R is false, and then we get to some contradiction, something that just can't possibly be true, then we've shown that R actually has to be true. So let's dig into this a little bit more. All right. So once we've worked through with the assumption that R was false, say we have something that we know is true, P. It might be a theorem, it might be some axiom, but we know it's true. It's a fact, all right? And after we assumed that R was false and we worked through some stuff, then what we've shown is that not P must be true. Well, if we have that we know P is true and we've shown that not P must also be true, then what we've created is the statement P and not P as a true statement. And we've seen before, back when we were talking about logic, that that's a contradiction. So since P and not P can't possibly be a true statement, then we have that our statement not R, so when we assumed R was false, not R, implies a contradiction. So now we have this new implication. So we know that the contradiction's false. So we have not R implies something that is false. And we know that that's true because we worked through stuff and showed that that was in fact true. So for an implication to be true when the thing that's in the position of C here is in fact false, then we know that our not R statement must also be false. So we must have false implies false. That's the only way that we have a true implication. So that means that not R is false, which means that our assumption was wrong and that R is in fact true. So that's the logic that's going on behind a proof by contradiction. And that's why we've waited so long to talk about it. Direct proofs have really simple logic behind them. Proofs by contrapositive have slightly more complicated logic behind them. Proofs by contradiction have fairly complicated logic playing behind them. So dig into this logic a little bit to convince yourself that it's actually sound logic so that you can actually believe proofs by contradiction when you see them and not be skeptical. So the way we define a proof by contradiction is when we show R is true by this technique of assuming R is in fact false and then showing that that implies a contradiction. And so we've got this true implication. That's a proof by contradiction. So let's talk a little bit about how this actually plays out. So say R is this quantified statement for all X in S, P of X implies Q of X. So a proof by contradiction would look something like not this, not R, right? Not this whole statement. And we're showing that it implies a contradiction. So let's talk about what not R actually says. So we've got not a universal quantifier, so it switches over to an existential quantifier. So we have there exists some element in our set S. And remember then the negation jumps over to the thing that the quantifier is working with. So we've got not P of x implies Q of x. Now remember, P of x implies Q of x is the same as not P of x or Q of x. So using De Morgan's laws, we can say that not that implication is actually P of x and not Q of x. So when we're working with a proof by contradiction, assuming not R, what we're actually going to do is we're going to say, hey, there's some element in x such that both P of x is true and not Q of x is true. And we're going to work from that, and we're going to work down until we've arrived at some kind of contradiction. So when you're doing a proof by contradiction, since the logic is so different than a proof by contrapositive or a direct proof, it's really important that you alert your reader that a proof by contradiction is coming. And that way they know what logic to expect from you. So ways that you might see this when you're reading are things like, suppose that R is false. Whenever you see suppose that it's false, suppose that the whole statement you're trying to prove is false, you know a proof by contradiction is coming. Or they might say, assume to the contrary that R is false. Or they might be so direct to say, for the sake of contradiction, suppose that R is false. All right? They might tell you that, hey, contradiction's coming. And I actually encourage you to be that upfront, that direct about it, because then that reminds you also when you go back and look at your own work, what type of proof you were working with. So the way this might play out, if you have for all x in S, P of x implies Q of x as your quantified statement R, then your proof might start with assume to the contrary. There exists some element in S such that P of x is true and Q of x is false. And then from there on, you're going to work to show that if P of x is true and Q of x is false, then there's some contradiction that arises. So let's take a look at some examples. So here's one. There's no smallest positive real number. Proving this directly or with a proof by contrapositive would be incredibly hard to do. But with a proof by contradiction, I can just say, hey, you know what? Assume to the contrary. There actually is a smallest positive real number. And then I can give it a name. I don't want to use a specific number because that's an example, but I can use some specific variable and work with that. So I'm going to say that the smallest positive real number is R. Well, then I think about it and I go, well, 0 is going to be less than or equal to R divided by 2, which is going to be less than R. So that means that R divided by 2 is a positive real number, and it's smaller than R. And that contradicts my assumption that R is in fact the smallest positive real number. So I have a contradiction, and therefore the original result I was trying to prove must in fact be true. Here's another example. If no odd integer can be expressed as the sum of 3 even integers. This is one that I could work through. I might want to work with like a proof by contrapositive, and then I'd have multiple cases involved, and it could be a fairly lengthy proof. I could get there though. But this one, if I look at it with a proof by contradiction, I say, you know what? Let's assume that that's actually, like, it's not true. So we're going to assume the contrary. So there's some odd integer that can be written as the sum of 3 even integers. So I'm going to give those even integers the names x, y, and z. I'm going to give my odd integer the name n. And then I'm going to use the definition of even to say x is 2a, y is 2b, and z is 2c. A, b, and c, they're all integers. So then I know n, my odd integer, can be written as the sum of the 3 even integers. So I've got n equals x plus y plus z. Well, that's going to equal 2a plus 2b plus 2c, which is equal to 2 times the quantity a plus b plus c. And since a plus b plus c is an integer, then by the definition of even, n is an even integer. So I've got n as an odd integer and n as an even integer, and that's a contradiction. So I know that the original statement must in fact be true. So here's another one. If a is an even integer and b is an odd integer, then 4 does not divide a squared plus 2b squared. So again, I probably could work this out directly. It would be a little bit messy along the way, and it would get kind of gross. And again, using the technique that gives you the cleanest, prettiest proof, that's the goal. All right, so in this case, a proof by contradiction is cleaner and more effective than a direct proof. So let's assume to the contrary. We've got some even integer a and odd integer b such that 4 divides a squared plus 2b squared. So I'm going to say a is 2x by the definition of even, and b is 2y plus 1 by the definition of odd, and I've got a squared plus 2b squared equals 4z by the definition of 4 dividing that quantity. So that gives me that a squared plus 2b squared is going to equal 2x squared plus 2 times the quantity, 2y plus 1 squared. And it's going to equal 4z by the definition of 4 dividing it. So I've got this complicated thing, and I'm going to go on and simplify it out a little bit. So I've got 4x squared plus 8y squared plus 8y plus 2 is going to equal 4z. Now, if I leave the 2 on the left-hand side and I subtract everything else across to the right-hand side, I'm going to have 2 equals 4z minus 4x squared minus 8y squared minus 8y. Well, I notice that everything on my new right-hand side right here has a 4 in common, so I'm going to factor out a 4. So I have 4 times the quantity z minus x squared minus 2y squared minus 2y. So now I have 2 equals 4 times some integer quantity. But that tells me that 4 in fact divides 2 by definition of divides. So that's not possible. So there's a contradiction, and my original result that I was attempting to prove must be true. So let's take a look at one final example. And you'll notice this is labeled as a theorem. It's in fact one of the most famous results in math that uses a proof by contradiction to show that it's true. So the statement, the result is the real number square root of 2 is irrational. So for the sake of contradiction, right, to prove it by contradiction, we're going to assume the contrary, that square root of 2 is rational. Well, by the definition of rational, then I should be able to write square root of 2 equals a over b for some integers a and b, where b is not equal to 0. I can go one step further too, and I can say, you know what, I want those integers to actually be in lowest terms, or a reduced fraction, all right? Smallest possible integers that I can have this here. So that means a and b, they have no factors in common. They've been reduced. So then I've got square root of 2 equals a over b for some reduced fraction a over b. So I'm going to square both sides and get 2 equals a squared divided by b squared. And then I'm going to multiply both sides by b squared. So I've got a squared equals 2b squared. Well, b squared is an integer, so I have 2 times an integer. That means a squared must be even. And I know that if I have a squared is even, then a also has to be even. So I can write a as 2c by definition of even. C is some integer. So I'm going to replace a squared with 2c squared. So I'll have 2c squared equals 2b squared then. So when I square 2c, I'm going to have 4c squared equals 2b squared. And I can divide both sides by 2, and I'll get b squared is going to equal 2c squared. Well, c squared is an integer, so that means b squared is even by the definition of even. And then I know that b must be even as well. So now I have a and b were in fact both even, which means they both have 2 as a divisor. So A over B wasn't actually the reduced fraction that I assumed that it was. So that's a contradiction, and that means that the real number square root of 2 must be irrational. A lot of times when we're working with irrational numbers, we want to either use a proof by contrapositive or a proof by contradiction, depending on the case. So direct proofs are rarely used with irrational numbers. Finally, I have a fun problem for you. All right. So we've got 3 prisoners. They're sentenced to long terms, but things are overcrowded, so one of them's got to be released. Warden says, hey, you know what? I'm going to blindfold them all, and I'll paint a red dot or blue dot on each of their foreheads. All right? So after he paints the dots, he's going to remove their blindfolds, and each prisoner is going to raise his hand if he sees a red dot on at least one other prisoner's head. And the first prisoner who figures out what color dot is on his own head is going to be released. So the warden blindfolds everybody. He paints a red dot on all 3 prisoners' heads. He removes the blindfolds. All of the prisoners see a red dot, so they all raise their hands. They actually all see 2 red dots, right? And then after a while, one of them finally says, I know what color my dot is. It's red. And that prisoner gets to go free. So the question is, how did that prisoner know that their dot was red? And what was the logic that was playing? Was it just a guess, or could he actually deduce it using a logical series of thought? I'll give you a hint. It's in this section for a reason. Enjoy.